Hello, everybody, and welcome to a brand new series that I'm titling Serious Science or Movie Magic. Today, and in this future series, we're going to be talking about a range of different sci fi movies, ranging from ones that do science so unbelievably well and so unbelievably accurate to ones that are majority fiction and are just for the fun of it. I want to do this series because I study physics. I'm Cooper Britain, I'm a third year physics student, and I feel like I can bring some sort of knowledge when I watch a lot of these movies. I feel like I understand them slightly more when movies come out, and I feel like I enjoy them more because I understand them at a lot deeper level than what a lot of people do, and I want to try and portray that knowledge and bring that knowledge over to you and give like examples and stuff. If I keep looking over to my right, it's because I have notes written on the movie that we're going to be talking about today. But this is the thing: when you're in school, physics is always around you. When you're in school, you are throwing a ball back and forth with your friends. You learn V equals IR when you're learning GCSEs, or whether you've been drunk before and you've tumbled down the stairs, which I know I have in the past. These are just some examples of like the fundamental physics and the fundamental science. But movies take this to another level. They use degree level, stuff that I've learned while I've been here doing my degree. And like I said, I want to try and portray that over to people who have seen these movies and potentially want to understand these movies a bit more. Today, we're going to be talking about Interstellar. If you haven't seen Interstellar, please don't worry. Take this as a reason, me trying to give you a reason to watch Interstellar and to understand it before you go into watching Interstellar. I've seen Interstellar quite a few times now. I had the opportunity to go and see cinema recently. It was phenomenal. But Interstellar is one of those movies where, as you progress through the movie, it gets quite hard to understand. At the beginning, it's a simple movie about trying to just help the planet and discover and create this new life for everyone. Whereas later on, you sort of get to some crazy physics concepts and crazy physics ideas. Interstellar is a sci-fi epic directed by Christopher Nolan that takes audiences on an exhilarating journey across space and time. Set in the future where Earth is facing environmental collapse, former NASA pilot Cooper, played by Matthew McConaughey, embarks on a daring mission alongside a team of astronauts to find a new habitable planet for humanity. Guided by a mysterious gravitational anomaly near Saturn, they travel through a wormhole to explore potentially viable worlds in a distant galaxy. As they venture into the unknown, the crew grapples with the challenges of interstellar travel, facing mind-bending phenomena like time dilation and gravitational anomalies. Meanwhile, back on Earth, Cooper's daughter Maeve, played by Jessica Chastain and Mackenzie Foy, grows up and becomes involved in the efforts to solve the planet's environmental crisis. Written by brothers Christopher and Jonathan Nolan, and starring not only the previous people mentioned, but also the likes of Anne Hathaway, Timothy Chalamet, Matt Damon, Michael Caine, and many more incredible actors and actresses. Okay, we're starting on this series on quite a high. I personally think this might be one of, if not the best science or physics movie that's ever been created. And it's not because the main character shares my name, which kind of plays a factor, but not too much. I think one of the reasons why this movie is so successful is it has a physicist directly involved in the making of the movie. Interstellar has incredible storytelling, it has incredible plot points, it has incredible music composed by Hans Zimmer, some of the best music. The Christopher Nolan movies always have incredible music, but this is just some of the best. But with this movie, when I watch this movie, it feels like it knows what it's talking about to an extent. And I know that's such a weird way to phrase it, but I feel like it comes across accurate without knowing that it's accurate, if that makes sense. Kip Thorne, who's an American theoretical physicist, and he won the 2017 Nobel Prize for physics. He was directly involved with this movie. He was the scientific consultant or advisor for the movie. There's so many behind-the-scenes shots where you can see him kind of writing stuff on blackboards for a lot of like the gravitational theory, which is a main plot point of the movie. And he did a lot of kind of that work for it. And then he's also listed as one of the executive producers for the movie. Afterwards, he also wrote a book called The Science of Interstellar, which basically just goes through all of the concepts used for the movie and breaks them down. Today, there's a lot of physics concepts in it. Today, I want to talk about one specifically. I want to talk about the extreme time dilation as a part of the movie where they approach a fictional black hole called Gargantua. Gargantua is depicted as being 100 million times larger than our sun. And there's also an accurate depiction of a black hole. Interstellar came out 5 years prior to the first actual image of a black hole ever being taken. And not only Interstellar, but the photo also depicts a disk of matter, of like gas and dust, and that offers light and heat to the surrounding planets. In Interstellar's case, the surrounding planets is Miller's planet, which is a water-based planet, which is kind of where the large time dilation part of this movie comes into play. With Miller's planet being in the orbit of the supermassive black hole, it is affected by this extreme time dilation, and 1 hour on the planet or within this black hole's gravity is the equivalent of 7 years outside of it. But before going into the crazy details, let's start at the actual beginning. What is time dilation? Time dilation is a phenomenon predicted by Albert Einstein's theory of relativity, which states that time can appear to pass differently for observers who are in different gravitational fields or moving at different speeds. There are two main types of time dilation: relative velocity and gravitational. Relative velocity time dilation occurs due to differences in speeds between observers. When moving in these high speeds, time appears to move more slowly. This is specifically when you're close to the speed of light, so approximately 670 million miles per hour. However, Interstellar displays gravitational time dilation. As they approach a black hole, or as you approach a black hole, the gravity becomes so intense and strong that it begins to affect space-time, warping length, width, height, and most importantly in this case, time itself. While something is under intense gravity, life would feel completely normal, bar this intense strain from the gravitational pressure, but time-wise, it would feel completely normal. You wouldn't feel like you're moving in slow motion, and you wouldn't feel like anything kind of different is moving in time. Whereas someone on the outside of this intense gravity, it would seem as you were moving in slow motion, or in extreme senses, you were just completely frozen in time itself. That's why the word relative is so important, because it's relative to whoever you are with, or whoever the main, what it's called, frame is. In shock horror, relative is important to relativity. Let's use an example from the movie. Out of the 4 crew members, only 3 choose to journey down to Miller's planet, with one of them staying in this main ship. It's important to note that the main ship is outside of Gargantua's orbit and is unaffected by this intense gravitational pull. 3 members end up being on Miller's planet for 3 hours and 17 minutes. When they arrive back on the main ship, it turns out that 23 years, 4 months, and 8 days have actually passed for this member on the main ship, and also Earth as well. So you can imagine that, especially as we were talking about before with Cooper and his daughter Murph, you're basically missing like 23 years of your child's life, which is such a crazy amount of time, and it plays a major part in like the kind of like tension of the movie.
Hello, Ron?
I've waited years.
How many years?
By now it must be.
It's 23 years, 4 months, 8 days.
Doyle?
But I was prepared. I knew the theory. Reality's different.
In a theoretical and hypothetical way of kind of observing time dilation, if the main ship was to take a telescope or binoculars and be able to look down to Miller's planet, it's unclear how far away they actually are between each other. Miller's planet and the 3 crew members on it would appear to be frozen in time. Another way of doing this would be if the crew going to Miller's planet took a video camera and they were live streaming back to the main ship or to Earth. The video would play back, but the video would appear frozen, as if there was like a very bad connection. However, over weeks and months and years, the video would actually play out what is going on in Miller's planet. And by the end of that time, if you took the entire 23-year-long video and you sped it all the way up, it would play out to almost like a normal speed and depict everything that went on. It's like, can you imagine watching a football game and having to wait 10.5 years for a 90-minute game outcome? Like, that's the scale that we're talking about. It's crazy. One interesting point about the sequence on Miller's planet is that the soundtrack actually has a ticking noise in the background, and the tick goes every 1.25 seconds. The ticking represents, well, the ticking when they're on Miller's planet, so this song plays when they're on Miller's planet. The ticking represents 24 hours passing on the main ship and on Earth, which I thought was just an amazing, like, it's such an interesting and amazing way to show this time dilation, to show how easy it is for these years to pass and for how how, because they know, they go down this planet knowing that this time dilation, and they know that 1 hour is 7 years, so they want it to be in and out by 1 hour, and it just shows like how easily this time passes and how easily this quickens on. And like I said earlier, it really adds to the intensity of the movie. I, in some research behind before this video, try to do some of the math behind it, and try to research a lot of the gravitational time dilation equations that are referred to with it. And I discovered there's a lot of different equations related to gravitational time dilation. A lot of them are for specific examples and specific references. For some examples here, there's a time dilation in reference to the Earth's surface. There's one for circular orbit and their associating gravities, and there's one for non-rotating spherical objects. The non-rotating spherical objects can actually be adjusted for black holes, but it'll eventually include something called the Schwarzschild radius, this being the distance from the center of the black hole to the edge of the black hole, but to give it its more actual technical names, from the singularity, which is the center of a black hole, to its event horizon, which is the edge of the black hole. I tried using this equation, like I said, to calculate the distance between Miller's planet and the main ship. However, when I did this, I realized that for this to work, Miller's planet would have to be at the middle of the black hole, so at the singularity, which in the movie is very much not at the center of the black hole, so it didn't work. The movie doesn't really give us much information. We obviously know what the time dilation difference is. We know that it's 100 million times larger than our sun, so you can take some kind of estimations from like the radius of the sun and things like that, but it's hard to actually mathematically prove. I wanted to try and mathematically prove this time dilation, but without having more information from the movie, from this fictional black hole, it would be very hard to actually prove it. Now, obviously, Interstellar is a science fiction movie. With all science has to come fiction, and as much as I say it's a perfect physics and science movie, it does have its very major part, and it's not even fiction, it's mainly like theory, which I guess kind of bleeds into fiction. However, I don't want to cover that today purely because it's nearing the end of the movie and it's like very major and heavy spoilers for the movie. And if you haven't seen the movie, if you're watching this and you haven't seen the movie, first of all, go and watch the movie. If I've not said it before, please go and watch it. It's something that you should. It's something that you should witness spoiler free, and I don't want to be the one to spoil it for you. Later on down the line, I might do one that's to do with that side of it. To do with the fiction or theoretical side of, well, the more theoretical side of Interstellar. But as of recording this, it's actually releasing in some IMAX cinemas across the country, and it's also available to watch nearly everywhere. So I watched in cinemas recently, as I said earlier, and it was phenomenal. So if I haven't convinced you already, I honestly don't know what else to say. So yeah. Anyway, thank you for watching this video. This is actually for a university project, so down in the description there's going to be a Google form that you can fill out. It should only take 4 or 5 minutes. It's just a few questions asking about what your information was going in prior to this video, have you seen the movie, things like that, and it would really help me out for things I have to do after this. So yeah, thank you for watching, hope you enjoyed, and I hope to see you in the next one. Bye bye.